So in this video we're going to calculate work using a dot product, and we're going to do 3 examples. We're going to do 2 examples where we're going to give one example where we're just given the vectors, and 2 examples where we have to come up with the vectors ourselves. But remember, in the previous video we said that work could be calculated if we just took the dot product of the force vector times the distance vector. So in this problem we're saying, hey, I have a force vector F equals 512, that's right here, and it's moving an object along a distance vector of 15.44 comma 2. So we're moving some object from here to here, and we're applying a constant force at an angle of 60 degrees, and we're given the vectors. So to calculate the work done, it is super simple. We just say the work is going to equal F dot V, and we've been given F dot V, so we don't even have to come up with it on our own. And so we're going to take the dot product of 512 with 15.44 comma 2, and then it's a dot product, so it's just 5 times 15.44, so 5 times that plus 12 times 2, and if you pop that into a calculator and crunch it, you get 101.2. And then all we need to do is make sure we put the correct units on it. So in this case we're told that the force being applied is in pounds and the distance we're moving is in feet. So this is 101 2/10 foot-pounds. So in this example it says, suppose a force of 20 newtons is applied to an object at a 45-degree angle over a distance of 10 meters. Find the work that was done. So this force here is a 10-pound force. We're being told that it makes an angle of 45 degrees with the object that's being pulled through the distance of 10 meters. So in this case we weren't given the vectors, but if we think about establishing an XY coordinate system, it's easy to describe the force vector, or sorry, the distance vector here, the distance vector PQ. If we establish an XY coordinate system, we can say, hey, it's a distance of 10 times, all we need is a unit vector in the direction of motion, and the simplest unit vector in the direction of motion is going to be the vector I, or 1 comma 0. So there's our distance vector. And then we just need to come up with the force vector. We know how large the force is. The force is 20 newtons, and we just need to multiply 20 newtons times a unit vector pointing in the correct direction. But the easiest unit vector in this direction comes to us from trigonometry. We say, hey, this vector, a unit vector at an angle of 45 degrees with the positive x-axis is just going to be the vector given by cosine of the angle comma sine of the angle. That's a vector of length 1 from trigonometry. This is a vector living on the unit circle. So this is the correct direction and this is the correct size. And because this direction vector has length 1, we now have a vector of length 20 in the correct direction. And to calculate the work done, we just take the dot product of those 2 vectors. So the work that's done is going to equal the dot product of the distance vector with the force vector, and the force vector looks like 20 times the vector cosine 45 degrees is going to be square root of 2 over 2, comma sine of 45 degrees is the square root of 2 over 2. And we can use now the properties of dot products to actually pull the 20 out front and multiply it by the 10. So the scalars can be multiplied to get the 200 times. And then the vector we have is, here is the vector 1, 0. And we're going to be dotting that with the vector root 2 over 2, comma root 2 over 2. And when we take this dot product, we get 1 times root 2 over 2 plus 0 times root 2 over 2. It's just going to be 200 times the square root of 2 over 2, which simplifies to 100 times the square root of 2. And we just need to remember to put the correct units on. And because the force is in newtons and the distance is in meters, this is going to be 100 square root of 2 Newton meters. So the last example, we have a sliding door that's being closed. It says a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees. Find the work done in moving the door 12 feet to the closed position. So I can kind of think of it this way. Here's the ground. The door sits here, and we've got a person down here pulling on a rope to close the door, and the door is going to move along into its closed position, and it's going to be traveling through a distance of 12 feet on its way to being closed. So I can kind of think of establishing a y-x coordinate system like this, where I make this direction positive y. We're told that the force makes a constant angle of 60 degrees with the door. So I pull on the rope. I'm going to pull and move with a constant force at a constant angle until I'm in the closed position. So I can do the same thing that I did before. The distance vector can be easily described using 12 times, if I make this the positive x direction, 12 times the unit vector 1, 0. The force vector is just going to be, hey, take the size of the force, which is 50 pounds, and multiply it by a unit vector in the direction of 60 degrees. But a unit vector in this direction is just going to be cosine of 60 degrees. This is a vector of length 1. Sine of 60 degrees from trigonometry. And to find the work done, I just take the dot product of those two vectors. So we're going to do f dot pq or pq dot f. The order in which you do a dot product doesn't matter. Remember, dot products are commutative. So I'm going to take 12 times the vector 1, 0, dotted with 50 times the vector cosine 60 is going to be 1/2. Sine of 60 degrees is square root of 2 over 2. And the scalars, the scalar product can be taken first. So we get 50 times 10 is 500. 50 times 2 is 100. So we get 600 from that. Times the dot product of 1, 0 with 1/2, square root of 2 over 2. And from there we get 600 times. We get 1 times 1/2 is 1/2 plus 0 times root 2 over 2, so we just get 1/2 out of the dot product right there, and so we get 300, and we just need to put the correct units in. We moved it 12 feet using pounds as our force, so this is 300 foot-pounds of work that was done.